Hi guys, I'm going to talk to you today about polynomial functions and modeling. I'm a little bit short on time because I have a Scholastic Bowl meeting coming up, so you might need to pause the video to catch up on notes because I'm going to kind of try to zip through this a little bit. First thing you need to know is, what does a polynomial function even look like? And this definition is really, really loaded. It has all these little subscripts, and what these guys are here, the a sub n, a sub n minus 1, those are just numbers. So it's going to look like this. It's going to be p of x equals, it's going to be a number, and it doesn't matter what the number is, but there's definitely going to be an x keep showing up, x, 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 and it's going to be to some power, plus another number, x to some power. And it can go on forever. That's why they used n, because it could start at x to the 100th, x to the 1000th. But you can keep going on until you just get plus a number at the very end, plus x and then plus a number. So these are coefficients, the numbers in front of the x's, and the degree, you need to write that down. The degree is what we call the highest exponent. And the leading coefficient is, well, actually, yeah, we can write it. The leading coefficient is the number in front of the degree, what we call term, the highest exponent term. The leading term is the same thing as the degree term, which is just the first term with the highest exponent, and then a constant is just a number. It's the number, usually it's at the end. Okay, the rules are for these powers, these exponents, okay? The exponent has to be positive. It can't be negative, and you can't have a fraction. So no negative exponents, no rational exponents, no radicals, no absolute values, no square roots of x, no 1 over x's, okay? All those things are not allowed. It's just a plain Jane x to an exponent. So let's look at some examples. Okay, you already know about some of these. The ones you already know are linear and quadratic. Those are the ones you really know. Constant's kind of a weird guy. We're going to kind of not talk about him very much. Write it down still if you want. But linear and quadratic, we already know. Okay, it is a polynomial, and what the linear is a degree 1. So if you have y equals 2x minus 5, the degree is 1 because that is the highest exponent. Okay, the leading term is the degree term, which is this whole piece. So that would be 2x. The leading coefficient is the number in front of the degree term, which is 2. And the constant is the negative 5. It keeps the sign. Okay, quadratic are the squares. So look, it's a degree 2. Kids, for some reason, want to forget quadratic. Remember the quadratic formula? It means x is squared. So there's an example. Okay, the leading term is 4x squared there. The degree is 2. The leading coefficient is 4, and the constant is 3. Then you have a cubic and a quartic example. I also think you should know a quintic is degree 5. And after that, you don't really need to know. We would just say a polynomial of degree 6. We would just say something like that, of degree 6. We don't have special names after quintic, really. Okay, so you might want to pause it and write down the polynomial names and their degree. If you want some examples, please write some of those down. So we know some things about quadratic functions. This is stuff we just finished up. If you have a function, if it's in factored form, we like it because factored form tells us the zeros, and that tells us the x-intercepts. The only difference between zeros and x-intercepts is we write x equals -1 and 3 for zeros, and x-intercepts, you write them as ordered pairs. Don't forget, you find the y-intercept by plugging in 0 for x, and it's always just that constant. How can you find a maximum and minimum? We use our calculator, second calculator max or second calculate min. The domain is all real numbers because there's no risk factors. And then the range you would get from looking at the graph and using that minimum value. Well, now we're going to apply this to more polynomials like cubics. So what we're going to do is if you have a function, you might not know how to factor it. So when we analyze, this is what I'd like you to write down. When you analyze polynomials, the first thing you would like is factored form. Well, what if you don't know how to factor? If you don't know how to factor, you could see if your calculator can help you. You could do second, calculate zeros, and you could find the zeros first, and then write the factors after. X-intercepts, you can also get from your calculate, second calculate zeros, okay, because that tells you your zeros and your x-intercepts. The y-intercept comes from the constant still. The max and the min come from the calculator still. That's second calculate max and min. And then the domain and range, they come from looking at the graph. First of all, the domain of all polynomials, because there's no risk factors, is negative infinity to positive infinity. Now, the range will be different. On the range, it depends on what the graph looks like. And we'll talk about that in just 1 second. Okay? Don't forget, when you do the max and min, you also use the y values, not the x values. But increasing and decreasing, if we were doing that, we would use the x values. It's also important to note that these have what we call relative max and relative min, because this graph, it goes down forever. So it technically does not have an absolute max or min. It just has a relative max and min just in the area. Okay, so let's look at these graphs. These are polynomials. You can tell because this is an x squared. This is just a constant, x cubed, and x to the fourth. Okay, what is the degree of this guy? It's the highest exponent. It's 2. The degree of this guy is 0. Of this guy is 3. And this guy is 4. So we know how to find the degree. It's the highest exponent. Now, all the rest of them, we're going to skip this one because it's kind of confusing. Leading term is the whole first piece. So for here, it would be x squared. This would be 2x cubed. And this guy would be negative x to the fourth. How do you find the leading coefficient? That's just the number in front of the leading term. So this would be 1, this would be 2, and this would be negative 1. And the constant is the number at the end, which would be 1 here. It would be negative 1 here. And this one, there's actually a plus 0 at the end. So the constant would just be 0. These guys on the next slide are not polynomials, and you can tell because they got some weird things going on. Absolute value, not a polynomial. Square root, not it. This is an x to the 4/5. I don't know if you can quite see it. X to the 4/5, that is not a polynomial. And anything with a fraction with an x in the denominator is not a polynomial. Okay, so what do we know about polynomials? Well, we break them up into 2 types. We have an even degree polynomial, and we have an odd degree polynomial. And you'll probably remember this pretty quickly. When you graph an even degree, we're looking at stuff with x squareds and x to the fourth and x to the sixth. The graphs are what we call either up and up or down and down. And that's talking about the end behavior. All of these graphs from outer space kind of look like a U. There could be little wiggles in here, but you might not see those wiggles if you were in outer space. So from outer space, they would just look like U-shaped graph. Okay, these are U-shaped. If it's an odd degree, we call these, Mrs. Bruno calls them these, no one else does, snake babies. You could have more wiggles in here if you wanted to. It could look like that or something really weird. But they look like kind of snakes. One's down, one's up. And this one is an up and then a down. And that's what I said is called the end behavior. How can you tell what your graph will look like? Well, the only thing you really need to know to help you figure out what the graph is going to look like is this leading term test. And what it does is it tells you what the end behavior will be. And these little zigzags in here just means that there could be lots of bumps in the road in the middle. You're only looking at those end pieces. So if it's an even degree, it will look like this if the leading coefficient, a sub n, is the leading coefficient. If it's positive. If it's positive, it's going to be an up and up. So if it's even and it's positive, it's an up and up. If it's even and it's negative, it's a down and down. If it's odd and it's positive, it's a down and up. If it's odd and it's negative, it's an up and down. So you might want to put that chart in your notes. So how can we tell just by graphing, by not graphing, like if you don't want to use your graphing calculator, which graph is which? Well, you'll see it's going to be pretty easy on the next page. The only things you need to look at is that leading term and the y-intercept. That's usually enough for you to figure it out. Because when you look at these graphs, I'm going to be like, okay, it's even, it's positive, it's an up and up. And the y-intercept is 3, so I just need to find the right graph. This one is an odd, so it's one of these snake babies. And I know since -5 is negative, it's going to be this snake baby, and there's a y-intercept of 2. This one is a positive snake baby, y-intercept of 1. This is a negative even, which is a down and down with some bumps in the road, with a y-intercept of 0. So take a look at these multiple choice on the next slide and see what you think. Can you find the graph? Sure. Which one is a U-shaped graph that goes up and a y-intercept of 3? Has to be D. How about this one? X to the 5th, that's an odd snake baby. Y-intercept of 1, it's positive. This one is A. This is a negative snake baby. Y-intercept of 2, that has to be B. And the negative U-shaped graph, y-intercept of 0, this one has to be C. So you can tell just by the clues of the graph what you're looking at. And that's the answers to that. Okay, so how do you find zeros? Okay, how do you know if something is a 0? You need to write this down. If a number is a 0, it's an x-intercept. And because you're going to do this on your homework, when you plug it into equation, it equals 0. When you plug it into the equation, it will equal 0. So let's look at some examples. Well, this first one, they did a really nice thing for us, and they actually factored it for us. So that's nice. You don't have to type it into your graphing calculator if you want. You can write it like this, which is factored, or the next guy. Well, I know what the zeros are just by looking at this. First of all, I have a 5 times an x times an x times an x to the x. That's a 5x to the 4th. This guy, you can also tell because it'd be like a 5 times an x cubed times an x, so it's an x to the 4th. That's why the graph is U-shaped. Even if it's factored form, you can still tell if it's U-shaped. The degree is 4, and the degree tells you how many you are looking for. That's how many zeros you are looking for. Now, if I look at my equation, though, how many can I find? Well, the 0 of this guy, x minus 2, what would make that 0 is 2. And the 0 to this guy is -1. So I only found 2, but I was looking for 4. Well, that's because this 2 actually came up 3 times. So we say that it has multiplicity 3. The number of times it comes up is what its multiplicity is. -1 only came up 1 time, so that's just multiplicity 1. You can tell by the exponent what the multiplicity is. And the way the graphs look can also give you a hint, because if you have even multiplicity, it will look different than if you have odd multiplicity. Okay, the first multiplicity was multiplicity 1, and that happened at -1. Do you see what the graph looks like, how it just straight passed through? Odd multiplicity, it passes through the x-axis. Okay, now 2 also had odd multiplicity. Its multiplicity is 3, but do you see how it passes through, but it hesitates first? If it's a higher multiplicity, it hesitates first. And that's what happens here. It does pass through, but first it hesitates before it passes through. Even multiplicities We call those bounce. They bounce on the y-axis, and higher multiplicities kind of hesitate first before they bounce. Like maybe it would look something like, instead of a straight bounce like this, maybe it would look like it's hesitating, and then it almost looks like it's a little flat at the bottom. Okay, so let's do some more practice. What do you do? Oh, here's what they said right there. If k is odd, if the multiplicity is odd, it crosses through. And if it's even, it bounces. They call it tangent, but I like to call it a bounce. And that's how you can tell. Now look at this guy. They want to know what the zeros are. Well, it's kind of sad because they didn't factor for it and you don't know how to factor it. So what do? Well, we're going to kind of work backwards. Your calculator can help you factor. First of all, what is the degree? The degree is 3. So I'm looking for 3 zeros. So type that into your graphing calculator and see what you get. X to the third minus 2x squared. Let's see if I got it here. X to the third minus 2x squared. Minus 9x plus 18. If you hit graph, you know it's going to be a snake, baby. And I don't need to see the whole graph because I see everything I need. I see those 3 zeros. Now, how can I find them? You can do second calculate 0. But these kind of look like they're nice. Sometimes if you go to the table, if you could see all 3 zeros, and I can here at -3, 2, and 3, that's even quicker. Or you could do second calculate 0. So I have -3, 2, and 3. Let's clear this up here. So I get -3, 2, and 3. What was their multiplicity? Well, their multiplicity was 1 because each one went right through, and I was looking for 3, and I found 3. There was no bouncing. So -3 multiplicity 1, 2 was multiplicity 1, and 3 was multiplicity 1. There was no bouncing. If I plug in -3 into this equation, I'll get 0. If I plug 1, or what was it? 2 into that equation, I'll get 0. Whatever you plug in as 0, you'll get 0. Okay, this one we did not get to in class today. I'm going to start that up tomorrow. But what happens here is when you're looking for 4, you actually only will find 2. And they're not very nice because we are supposed to factor this one with the u substitution. And this one actually has some imaginary roots. We have some imaginary roots because this is a poser problem. So it's u squared plus 4u minus 45, which is a u plus 9 and a u minus 5, which means u equals -9 and u equals 5. But u is the same thing as x squared. So x squared is -9 and x squared is 5. So actually, when you square root both of these, I get plus or minus 3i for 2 of them, which are imaginary roots. And we'll talk more about that soon. And we get plus or minus square root of 5. These would not show up on the table. And if you did second calculate 0, it would show you some really nasty stuff, really nasty decimals. So this one you had to do by hand. Sometimes we will have to do it by hand, but you will know, and I will help you factor those when that comes up. Okay, the only other thing that we talked about in class today is if you are using an equation, like in a word problem or something, and they're asking you to plug in multiple values, it is not easy. I mean, it's easy, but it's so boring to plug every single thing into this equation multiple times. Plug in 0, plug in 0.5, plug in 1, plug in 1.5, all the way to 6. You don't want to do that. If they ask you to plug in multiple values, they're telling you to use your calculator and the table. If you just plug this into your equation and you go to the table, it will plug them all in for you. Okay, and that's mostly it. We have some word problems here, and we will have some time to do some homework questions when they come up later this week.